we look at impulse, and in the case of two objects colliding, we have our change in momentum of object 1, the force it experiences, and the time of the collision. And then we'd have the same thing for object 2, force times time over here. And what we know is by Newton's third law that the force that they exert on each other is going to be the same. And we also know that time for the collision, because they're both involved in the same collision, they're both, going to stop in the same amount of time. So we can say that our change in momentum 1 is going to be equal to negative change in momentum 2. And the reason we're going to include the negative there, right, is because they're changing momentum in opposite directions, especially, think like a head-on collision here or something. Their forces are going to be exerted in equal and opposite directions, so the momentum is going to change in opposite directions. So that means that delta P1 is not equal to, but plus delta P2 is equal to 0. And that means that my change in momentum is 0. In other words, there's no total change in momentum in the system. So that means that my total momentum, which is momentum of object 1 plus momentum of object 2 at any point in time, is constant. So that means that we can say that momentum of object 1 plus momentum of object 2 before a collision is equal to momentum of object 1 plus momentum of object 2 after the collision. So we use the little asterisk here, we call it prime, like P1 prime, P2 prime. The primes indicate after the collision, no primes would indicate before, and this is essentially our equation for conservation of momentum. Okay? That my total momentum before anything happens is equal to the total momentum after any particular event. Now this can be true for things moving in multiple dimensions as well. So for example, if we have a collision between two objects here, here's object 1, and here's object 2 before the collision, so object 1 is going to go and hit object 2, but not exactly dead on, and so afterwards, object 1 is going to be moving this direction, while object 2 would be moving that direction. So there's our kind of before and after situations. And the way we deal with this is just kind of the way we dealt with things in kinematics, where we separated things into x and y. So what we can say in our setup is that momentum of object 1 in the x direction plus momentum of object 2 in the x direction before the collision is equal to momentum of object 1 in the x direction after plus momentum of object 2 in the x direction after the collision. And then we'd also set it up for the y direction, momentum of object 1 in the y plus momentum of object 2 in the y direction is equal to momentum of object 1 in the y direction prime plus momentum of object 2 the y direction prime. And so by separating things out into the different directions, then we can solve for, say, how fast these things are going after the collision or something along those lines. So if we have things where things are traveling in multiple dimensions, we just split them up into their x, y. If we're doing 3 dimensions, maybe a z direction. And so by splitting it up like that and considering each direction independently, we can say that momentum is conserved independently in each direction. Now, systems are very important in a collision, so it's kind of really important that we think about this idea of systems. Conservation of momentum is only true in what we call isolated systems. What that means is that there are no outside forces involved. In other words, once we pick our system, there's no forces acting on that system from outside the system. Everything has to be included in that system in order for conservation of momentum to work. So let me give you an example of that. So here's kind of a complicated example where we have a rocket. It's going to fly in this parabolic path, and then sort of right here, we're going to have, you could think of this as a collision where two things are going to go off in separate directions. So started together, going off. And what we see is that momentum is conserved in the x direction, but not in the y direction. And so we want to look at the reasons for that, and it has to do with this idea of isolated systems. So our system of interest is the rocket itself, right? There's before, there's after. The circles represent our system. Well, in the x direction, as we know from projectile motion, in the x direction, there is no net force acting on this rocket, right? Our velocity, remember, was constant in that direction. So because there was no force acting on our rocket in the x direction, momentum is conserved. However, in the y direction, what's acting on it? Well, gravity is the entire time. Well, gravity comes from the interaction between the rocket and the surface of the Earth there, and from the mass of the Earth and the mass of the rocket interacting gives us that force of gravity. That is outside of what we've defined as our system of interest. So that means that momentum in the y direction, where gravity is acting, is not conserved in the way we would expect it to be because of this outside force. So in order to use conservation of momentum, you have to be working in an isolated system. In other words, there can't be any outside forces acting on whatever our system of interest is.